All right, in this inertial mass inquiry, we have a pretty elaborate setup here. We have a mass that we're going to drop and let it fall. Now there's a string attached to it. It goes up over a pulley, up over this pulley, down underneath this pulley, and then it's wrapped around an axle here that spins this table. And we want to figure out the rotational inertia I of this table. The reason we want to do that is because on this platform we can actually put some other objects. I can put a disc on there, I can put a ring on here, and then we can do the experiment again and get a calculation for I every time, so I can figure out the I of various objects with this entire device. So we need to derive an equation to use for this device. And the mass is going to be falling down through these two red things here are photogates. So we're going to drop it down through the photogates, so it's going to know how much time it took to fall to get to the ground. Technically, this would be like the ground here. Okay, this isn't exactly the way we have it set up, but it's the same concept. So we're going to drop this mass through these two photogates. We're going to get a time, how long it takes for it to fall. Okay, and then we're going to we have another photogate actually. I should make this a little bit more obvious. So we have another photogate attached right here that then goes to a computer. And this is going to tell us, it's going to tell us what the final angular velocity is of this thing. So that's how we're going to get all this stuff. So we need to try to derive a kind of a complicated equation. Now the thing to remember is that the mass here that's falling, we're going to drop a 0.5 kilogram mass. So there's the mass, and then the radius of this where we're applying the torque. So this force is going to be applying around this thing right here, and there's a radius of this axle. The radius of the axle is 1 centimeter. So the radius is 0.01 meters. We're going to use those in our derivation. So the way we derive this is we still start at the beginning with torque equals I fish. And torque we know as F times R equals I fish. And so the I is going to equal the force times R over the angular acceleration. So we can start plugging some things in here to figure out for I. So one of our difficult things is, what is the force that's going to be spinning this thing? Well, you might tend to think that it's equal to the mass of the dropping object times gravity. That'd be the weight of the object. And that is a real easy thing to think about. And that's, this weight pulling down here is actually being transferred over here to this wheel, and so it should be all the weight doing that. The problem is that people always forget that not only is the weight spinning this thing, but the weight is also accelerating itself. It's accelerating itself. For this object to be accelerating downwards, some of the force needs to be doing that. So this is not it's attached by a string to this. So some of the force is going to use to spin it. Some of the force is going to be used to accelerate itself down. How do we know how much force that is? Well, it's going to be the mass of the object times whatever its acceleration rate is. See, it's not falling at 9.81. Mass times gravity is the total amount of force available, but I'm going to subtract out the mass of the object times its own acceleration rate. So this force right here will be the amount of force that's actually causing this object to spin. This is the total force available by a weight. I'm subtracting out the force needed to accelerate itself, and whatever's left will be the force that's spinning this thing, which is what we want. So this right here is kind of my equation for force that I need to put into this equation. So I have now I equals, and then I'm going to put this force in for F, and I'm going to multiply it by R. So I'm going to distribute the R through there. So it's going to be M times G times R minus M times A times R, right? All over the fish. Okay. Now this next thing is a little confusing also. Right here on the top, we have a linear acceleration. That's the acceleration of this mass falling down. How does that correlate to the angular acceleration of this? They're attached by a string, so the linear acceleration of this it correlates to the angular acceleration of this. And if you remember how that works, linear motion is the angular motion times r. So, and this works for everything. So linear angular displacement is angular displacement times r, and velocity is angular displacement times r. You take the rotational variable times radius to get the linear version of it. So in for A, I can actually put fish times r. So I'm going to do m times g times r minus m, and in for A, I'm going to put fish r. So I'm going to have fish times, and that'll be an r squared actually, okay, all over fish. All right, so now I can do m times g times r divided by fish minus, and I can cancel out a fish there as long as I keep the fish over on the denominator of the first one, so minus mr squared. Okay, so I get an equation, fish, so this is going to be I equals m times g times r. Now if you remember, fish is final angular velocity over time, because it's actually final angular velocity minus initial velocity, but the initial velocity is 0. So fish is butt f over t. So if this is over fish, it's going to be t over butt f. And this is minus mr squared. So if I put in 0.5 for the masses, I put in 9.81 for the gravities, I put 0.01 in for the r, then, and you can do this math, you will get 0.049 times, the time, all over the final angular velocity, minus, and this would be 0.00005. So there is our equation for our setup in the lab. If I want to figure out the rotational inertia of this wheel or anything on the wheel, I'm going to just drop the mass. I'm going to take 0.049 times whatever the time was it took, divided by the max angular speed of the platform, and minus this 0.00005, and I'll have a calculation for the rotational inertia of the item.